Hi, I'm Sam Hunsel, and I'm going to present on Euclid's Book 1 of Euclid's Elements, and more specifically go into a proof of the Pythagorean Theorem. So what is Book 1? I know there's a presentation before this one about who Euclid is and like more of the history on Euclid, so I would suggest watching that before watching mine. But just something brief that I think you should know for this, that there are 13 books of Euclid's Elements, different ones where he goes into propositions. Book 1 has a lot more definitions. He describes his postulates and common notions in this book, which he doesn't in the other books. But also it's important to note that not every idea is Euclid's, especially in this first one. He did not come up with everything in this book out of thin air, but he does provide a lot of his own proofs and ways of solving his propositions that he lists. He also organizes them in a logical fashion and geometry that like builds up. And it's the reason why the Pythagorean theorem is in this book. He obviously didn't come up with it, but he does provide a really neat proof of it that we'll look at towards the end of this presentation. So yeah, like I said, there are 23 definitions, 5 postulates, and 5 common notions, which what we would call axioms these days, and then 48 propositions, and the last 2 are the Pythagorean theorem and its converse. The book 1 really focuses on plane geometry, which is just the geometry of a figure on a flat 2D surface. So we look at flat surfaces, we look at straight and parallel lines, triangle congruences, even some parallelograms in there towards the end, and then of course the Pythagorean theorem. So he first starts off with his definitions in this book, and here I've listed them. I'm not going to read through all of them. You can do that on your own time if you'd like. Pause the video, take a read. But these are written for someone who is just learning to study geometry, but we have to be careful because the language he uses in these definitions and in his book completely aren't exactly the way that we know things. So the modern way we would say like a line, we would usually think of a straight line, and that's actually his straight line when he says that. His line means like a curve, like a parabola curve in ours. And so that's kind of interesting to note. Also, I always find it funny that definition 1 is of a point, and it just is a point is that of which there is no part. So it's just saying like a point is nothing, which is kind of funny, which we use points a lot in the rest of his postulates. So I think that's kind of an interesting thing to point out. So his postulates and common notions are ideas that are like rules for the geometry is working in. So we could have different geometries that have different sets of rules, and it won't look like the geometry that you and I are used to. His postulates are those rules, and then his common notions are things that are kind of expected to happen in his geometry. So for one, the common notion number 1, things equal to the same thing are also equal to one another. So it's if you have 2 things that are equal to one thing, then those things are equal. Same with a postulate is that like in postulate 1, it says, let it have been postulated to draw a straight line from any point to any point. So that just means he thinks that if I have 2 points, I can draw a straight line in between them. And I can do that for any 2 points. So these are things that he has as rules for his geometry. The only postulate that's kind of important that I want to highlight is the parallel postulate. It's his postulate 1.5. And so I'm going to go ahead and read it for you. And that if a straight line falling across 2 other straight lines makes internal angles on the same side less than 2 right angles, then the other 2 straight lines being produced to infinity meet on that side of the original straight line that the sum of the internal angles is less than 2 right angles and do not meet on the other side. And you're like, whoa, what does that mean? There's a lot of words there. So I'm going to go ahead and just kind of use the figure to draw it out. So here's our straight line that he talks about first, right here. And then he has 2 other straight lines. We're going to go ahead and do those in green. So he has 2 other straight lines, and this first, the blue straight line falls across the 2 green straight lines. He has 2 internal angles, beta and alpha, and they make the angles on the same side, and they're less than 2 right angles, so they're acute angles. Then the other 2 straight lines, which are the green, being produced forever, will eventually meet at a point on this side. That's all he's saying. So he's saying if they're not parallel, they will meet eventually on one side of the line. It seems kind of intuitive, this thing, but it's actually hard to prove and very highly debated because the proofs are kind of elusive and don't make as much sense. But it does turn out that this postulate is very important. If Euclid did not include this postulate in his geometry, or the postulate was false, so this wasn't true, it's actually called non-Euclidean geometry. And geometry where this proposition is independent from this is called an absolute geometry. So that means the other propositions don't rely on this parallel postulate. That's called absolute geometry. And so that's kind of intriguing. So first, we're actually going to look at all of the propositions. And I have them all listed in each slide. And this is actually from my geometry book that I took in the college geometry class here at Truman. That does a really good job of listing them all off. I'm not going to read through all of them. That you can do that if you would like. But the reason it says like in the propositions theorem 21.1, theorem 21.2 is because in the book that I used, we had to prove these things eventually. And so like proposition 3 says theorem 8.8, and that was one that we had to prove. So it's just referencing them to other theorems in the book. But propositions 1 through 4 kind of start off with constructing an equilateral triangle and defining congruence of lines and what it means, starting at the basics of lines. And actually proposition 1.4 is the side angle side theorem from modern geometry. So it says if you have two triangles and they each have a congruent side, and then that angle within the congruent side is also congruent, then you have two congruent triangles. And so that's pretty cool that he does define that. It's very wordy in his words, but that's what that one is. Propositions 5 through 7 definitely go into isosceles triangles. So you can prove the isosceles triangle if you have two sides that are congruent, then the angles are congruent, and the converse as well. And then the 7th proposition is often called the hinge theorem because it deals with 3 hinges of lines. And so you can give those a read if you would like. Propositions 8 through 28, there's a lot of them. There's nothing very specific about them besides they continue to build on triangles, angles, and lines. He starts defining all sorts of things relating to the angles of triangles and angles of lines. And it's actually the last of Euclid's absolute geometry. So after proposition 28, he has to use his 5th postulate, the parallel postulate, to be able to prove his other propositions. And then the last few here, I'm going to go ahead and move my little screen there so you can see. The last of the propositions, 29 through 48, is still more about triangles. He introduces parallelograms because we do have the parallel postulate in these propositions, and so he's able to use things with parallel lines and defining things about those angles. And then 47 and 48 are the Pythagorean theorem and its converse, and we will look and go ahead and do Euclid's proof of this Pythagorean theorem here. I'm going to go ahead and move that back. Next slide. Okay, so the Pythagorean theorem. We're going to first look at Pythagoras' proof of it so you can kind of compare the difference between this one and Euclid's. It was thought that Pythagoras proved it somewhat like this figure here by the method of dissection. So we have a right triangle with sides A, B, and C. We start off with a right triangle here. And so then we can see that since this side length is C, the area of this square here is C squared, the inner square. That makes sense. If we stack our right triangles around, so it forms a small square in the middle and we form a larger square outside, we can say that the area of the large square is A plus B squared, right? Side length times side length, A plus B squared. So that's the area of the large square. But we can also say that the area of the large square is C squared, the area of the small square, plus the areas of the 4 triangles, right? So it's just, get my pen color here. It's just the area of this square, large square, and then added to the areas of the small triangles here, and that also makes the large square. And so it turns out when you set those two areas equal to each other and solve and do some algebra, you will get the Pythagorean theorem, a squared plus b squared equals c squared for a right triangle. So that's all cool, and that uses just like simple areas and geometry. Euclid uses a proof now by windmill, and it just looks kind of like a windmill, and that's why it's called that sometimes, as you can see in the figure here. He uses it by drawing lines and using areas of squares and triangles. And so he uses all of his propositions. We're going to go through the proof. There's two parts. The second part is very, very similar to the first part, and we'll get there eventually. But so starting off, his proposition 147 says, in right angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. So his overall goal is this. He has a triangle ABC, and you can see that right here. He says, well, if I can prove that the area of the square on the side subtending the right angle, which means this large guy here, BCED. If I can say that this area is equal to these two smaller squares, then I have proved the Pythagorean theorem. Now, why is that? Well, if I have sides A, B, and C, they're squares. So my area here is C squared, and my area here is A squared and B squared, right? So he says I need all these I need the area of the large square to equal the area of the small squares. So what he does is starts off with a right triangle, right? We start with the triangle ABC and then construct those squares on the sides of the triangle using proposition 146, which I'm not going to state what each proposition says, but if you don't believe me, you can go and read the proposition for yourself since they're in the slides or in the video here. You can go back and look at those if you want. So he does that using his proposition 46. Now we wish to prove first in part 1 that the area of BCED is equal to the sum of the areas ABFG, ACKH. All right, now that's the overall goal of the Pythagorean theorem. Now we employ proposition 31 to draw a line AL through point A that is parallel to line BD. What does that mean in terms of our picture? That means we have line AL through point A, right here, that is parallel to line BD. They don't ever cross. That's what that means. So now, looking even smaller, our goal is to prove that the area of ABFG, the square ABFG, let me get a different pen color. ABFG, this square, is equal to the area of rectangle BDLM. We wish to show that these two areas are the same. Okay. And also, we want the areas of ACKH, get a different pen color, this larger square here, ACKH, equal to the area of the other half of this large square, CELM, right here. So those are the areas we're trying to look at here. So now he notices that CA and AG are on the same line. I'm going to erase this pen here. He notices that CA and AG are on the same line. And this is because angle BAC right here is a right angle by our construction, by the right triangle we made. And GAB is also a right angle because we made a square. So by his proposition 14, we know that line CG, this whole thing right here, is straight, and so CA and AG are on the same line. So that's what we've got so far. Now he wants to use side angle side to show that two triangles are congruent. Okay, and here's what he's going to do. By postulate 1, so his rules of geometry here, by postulate 1, he draws line segments AD, new segments AD and FC to make two triangles, okay? These triangles are A, B, D in the red, and F, B, C. And you can see by a picture that they kind of look congruent here, but we're going to prove that using side angle side. So since these triangles are on the side of the same square, line AB is congruent to FB, and in the same way, BD is congruent to BC. So basically he said, okay, these triangles share a line. One right here, and they have the same side of a square, and squares have the same length of sides, so that means these lines are congruent. He also said, so the angle of ABD, a different pen color here, the angle ABD equals the angle of ABC plus right angle CBD of the square. And in the same way, FBC is equal to ABC plus the right angle FBA because of this square right here. So by postulate 4, ABD is congruent to FBC. So I'm going to erase the pen here and show you that. So looking at our triangles here, we have triangle FAC, ABD. We have that now these two sides are congruent, and we now have that these two angles are congruent. Okay. Okay, and we also have here that these two sides are congruent because they're also on the side of the same square. So it's the same way. So now we have two congruent sides with a congruent angle. And so by proposition 4, which is side angle side, triangle ABD is congruent to triangle FBC. Okay. So by proposition 41 now, the area of triangle ABD and the triangle, the area of triangle ABD and rectangle BDLM share the line BD. That's this one right here, BD. This rectangle, this small rectangle, here, let's just erase the pen. He's saying that this small rectangle and this triangle share the same side, which they do, this side right here. And it falls between parallel lines BD and AL. So the rectangle of BDLM is 2 times the area of ABD. Thus, in a similar way, the area of ABFG is 2 times the area of FBC. And that's by his proposition 41, okay? Since those two triangles are congruent, we thus can set up an inequality so that the area of rectangle BDLM is 2 times the area of ABD, which, since the triangles are congruent, we have the area of FBC equal thus to the area of AFG. So we have sought out what we proved in part 1, which is that the area of rectangle BDLM equals the area of this square ABFG. And that's what part 1 proved by setting up triangles. Okay, now in part 2, he does the exact same thing. So he would want to prove that the area of the rectangle CELM is equal to this area of the large square. He uses similar properties in thinking as part 1. So he draws lines AE and BK and looks at triangles he draws those lines, and then he looks at triangles ACE and KCB. Okay, and this I am actually not going to do because it is very similar. He goes along in the same exact way. Triangles are sharing sides. He uses triangles are sharing angles. He uses side angle side to prove this. I would encourage you to try it yourself if you can, because, and he uses the same propositions to show those things too. So we eventually get that these two triangles are congruent and that the area of one is, or the area of one square is 2 times the area of the other triangle, and he does the exact same thing with this. So I'm not going to prove that part. And then eventually he has the area of the triangle of this rectangle BDLM equal to the area of square ABFG, the blue here in this picture. And so thus we have that the area of rectangle BDLM is the same as ABFG. That was the part that we proved in the first, oh, I'm gonna erase this. The part we proved in the first part here. We had that these areas are congruent, are the same in the first part. And in the second part, we went and we showed that these areas are the same. And so when we substitute those in, we have that the area of the large square is equal to the sum of the areas of the smaller squares on the sides. And so thus, the area of the square on the opposite side of the right angle is equal to the sum of the areas of the other squares on the other two sides. And that's how he proves the Pythagorean theorem. It does involve a lot of propositions, which, because the propositions kind of build on each other since he put them in the logical area or in a logical fashion, it does take a lot to be able to prove the Pythagorean theorem for Euclid. It's actually a very nice, clean, simple way of doing it, just drawing some lines, using some triangles, looking at the areas. And he's credited well with coming up with this windmill method. And then these are the references I used.